So we are on video 24 and we're talking about convergence of series. And there's some hints at the top of the worksheet. And I'm going to talk about those first, and then I'm going to get into some of these different terms that are on the worksheet itself. Okay, so first of all, let's say, let me write this down first. All right, if a particular series diverges, and we're going to call it A sub n, we're going to label the pieces A sub n. If that diverges, and those pieces are all smaller than each, you know, if you can line them up one at a time and they're all smaller than a different series terms, then the larger one also diverges. Now, if you'll note in your worksheet, it also has an equals, which is obvious, and there's a less than 0 on this side, which is necessary because otherwise some rascal is going to say, hey, I can make it negative and mess up everything you're talking about. Well, yeah. We're only talking about positives. And of course, if this is equal, they'll both diverge. Duh. So this is really the only time you're really thinking about it as being useful anyway. And similarly, we're going to keep that condition in the same order and switch this around. We're going to say if the B's converge, then the A's must also converge. Right? If BN's converges, then the AN's converges. Yeah, whatever, the way I wrote it. Okay, so this makes sense because if you have a bigger series and it converges and everything's greater than 0, blah, 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 then the smaller one also has to converge, right? That kind of makes sense. So those are two things we're going to rely on as we work through, and you can think of this visually. You can say, hey, we know this about integrals too. I don't know why I'm having so much trouble drawing lines today. There we go. If you have this being, let's say, the larger one, and that integral converges, we know that this integral has to converge also. And if the blue one diverges, then the red one diverges. So I think we've said this before. So this is the same thing, only with series. Okay, so the plain old vanilla comparison test that you would use would just be to compare term by term, just like what that definition said. So let me give you some hints. If you have, x is greater than 0 and y is greater than 0, just so this makes sense, all right? You have some kind of expression that's like 1 over x. And I'm just using x to mean a whole expression. That could have a whole expression with lots of stuff in it, but it's something. You're comparing it to some other fraction that has the same numerator, and it's going to be like x plus y, right? Just keep in mind that the bigger denominator gives you the smaller fraction. Okay, it seems like a little thing, but it's a big thing because it's very easy to mess that up when you're going too quickly. Just take your time, go through these slowly, think them through, and just remember fraction denominators do the opposite of what the numerators do in terms of greater than or less than. All right, so that's your first thing. All right, the next little hint is that if you have sine or cosine, it lives in a world between 1 and -1. So if it's in the numerator, even if you square it, like if you square it, then like it still lives between 0 and 1. So if you have any of that stuff in the numerator of a fraction, okay, so whatever is here, if you have, sine or sine squared or sine, even sine times cosine, that kind of stuff, and then you have gobbledygook. X squared plus 3x plus n plus q. I don't care what it is. It's under there. You just know that you could just, copy and paste this whole thing and just being ridiculous. Your expression is not going to have multiple variables. I'm just saying that, okay? It doesn't matter what's in there, that you know that it's wedged between 1 and -1 of the same gobbledygook. Whatever that gobbledygook is, you could just put it like that and just sandwich this guy directly between a 1 and -1, maybe put some equals there just for safety. And then if you can prove anything about both ends, like about convergence, then the guy in the middle obviously has to converge also. So that's one of the things you should keep in mind. And along that same discussion line, if you can prove that if you can get rid of the negative signs and make everything positive and it still converges, then it converged with the negative sign. Let me try to explain this. Let me just start with a really, really simple example. I think you all recognize that this, if they were all positive, that thing would converge to 1. So you're taking a half, and a half of what remains of that, which is a half. So like you're adding up to 1. Okay, but what's happening here is every other piece is positive and every other piece is negative. So since S2, which is equal to 1/2 plus 1/4 plus 1/8, yada, 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 if that adds up to 1, okay, since that adds up to 1, then S converges to something. And we can solve for that, but that's not our job today. Our job is to just determine if it does converge. But it has to converge to something, because if all the terms for S2 were positive, then you get 1. If all the terms are negative, like if you flip them all to being negative, you'd get -1. So it actually doesn't matter how many of these terms you flip. You still, like, you can flip a finite or infinite number of them. It doesn't matter. You can make them in any pattern you want. It doesn't matter. You're still going to land somewhere between -1 and 1, so therefore it will converge regardless of what kind of crazy idea you have for how you're going to flip the signs. It's still going to converge, because there's not enough bulk in this whole thing. Regardless of if you flip the signs, you can't get outside that zone from -1 to 1. Okay, my handwriting is a mess, so I'm just typing this out. If a series is absolutely convergent, which means if we were to take and put absolute bars around each individual term like this, and it's still convergent, then any type of sign flipping can't hurt that, okay? All right, that should be enough to get you through problem 1. But now we're going to go to problem 2 and talk about the ratio test. Okay, so this is a really cool thing, and I want to set it up. I want to motivate it by giving you an example. What about if you have, let me just write it down. Let's say you have from, it doesn't have to be 1, it could be any number, but any integer you want up to infinity. You can chop off the first 1,000 pieces if you want. It doesn't matter. The question is whether the tail converges. We really have no concern about whether the first 100 pieces. You can take the first 100 or 1,000 terms of this and add it up. It will be a number. The question is whether the tail goes off to infinity, even as the terms themselves might be decreasing. Okay, that's what we're asking. So let's say we want to know if this guy is converging. So first of all, let me just compare for you n squared. So I'll talk about ratio test in just a second. I want to compare n squared versus 2 to the n for just a second, and sort of motivate this cell for the numbers 3, 4, and 5, so we can get a feel for what's going on. So 9, 16, 25 is how n squared is going to progress, whereas 8, 16, 32 is how this other guy's going to progress. So you notice what I did is I found the place where this crossover occurs. Now, the question is, do you know for sure that n squared is always going to stay smaller than 2 to the n, and will it stay sufficiently smaller that this whole mess over here converges? And it will, but how can we prove that? So there is a special little test called the ratio test that allows us to quickly tell whether this thing works. And now let me write that down for you. Okay, so the ratio test says you have to find this limit, and then if L is greater than 1, it's a divergent situation. And it's really obvious why that's true, because the pieces are actually kind of getting bigger, right? And if it's going to down lower than 1, some limit between 0 and 1 really, but you have the absolute value symbol, so it means between 0 and 1, this is going to be convergent, and L equals to 1 is unclear because you have to do more digging. It might be what's called convergent or divergent. I'm going to put it in the same order, or it could be something in the middle called conditionally convergent, which we'll talk about in a second. But for now, I want to just know, I want to show you what happens when we don't get the L equals 1 situation. Okay, so let's go ahead and calculate what happens for our little friend here and see which situation we end up with. So I'm going to leave that over here. Now, if this a sub n is equal to n squared over 2 to the n, what does this look like? A n plus 1 over a n. I'm going to ditch the absolute value sign. It's kind of stupid because everything we have is positive, so we don't have to worry about that. And the thing that we're dealing with is already in a fraction form. So I'm going to just take the second fraction and flip it. So first of all, I'm just writing a n plus 1, and then I'm going to flip a n and write it here. And that's my first step. Okay, now I'm going to do a little calculating and say, well, we get a 2 down here, obviously. But what about what's going on up here? I'm going to actually put this n squared back inside there. So I'm going to rewrite this as n plus 1 over n, square the whole thing. It's just going to make my life easier. All right, and then I'm going to rewrite that as 1 plus 1 over n, that whole mess squared over 2. And now we want to take the limit as n goes to infinity of this mess, and now it's obvious that it's just 1/2, which is less than 1, so this whole thing is absolutely convergent. And I'm not using grammar to just be emphatic. Okay, it means it can converge in the absolute sense. It converges. It does not require any kind of sign flipping to cause it to flip. But since it's completely positive, it's redundant to say it's absolutely convergent, because anyone who's looking at that knows if it's convergent, that's what you mean. You mean convergence in the very strongest sense, where the order of the terms does not matter, and you could take the terms in literally any order you want. I want to kind of emphasize that before I talk about conditional convergence. Here we have the alternating harmonic series, and that is the canonical example of a conditionally convergent beast. And let me just demonstrate to you why this is the case. You can say S plus, for example, and here's all the positive terms, right, is equal to 1/2 of the full harmonic series. You see, so if the harmonic series converged, then that all those positive pieces would converge, and that would be finite. But they both have to converge, or they both have to diverge. They're off by a factor of 2, but what's a factor of 2 when you're talking about infinity? And the same thing can really be done with the negative side. So you can say negative 1/3 plus 1/5 plus 1/7, blah, blah, blah. And you can use exactly the same proof we used before, but let's just make our lives a little easier. Instead of just adding 1/2, 1/2, 1/2 like we did before, we can just add 1/4, 1/4, 1/4. So for example, we can say this first piece is greater than or equal to 1/4. These two pieces added together is greater than or equal to 1/4, and then the next 4 pieces and the next 8 pieces and so on and so forth. And as long as we keep adding 1/4, 1/4, 1/4, we can get to infinity. So the positive pieces comprise positive infinity, and the negative pieces comprise negative infinity. So if you have a pile of positive infinity and a pile of negative infinity, I like to think about cars trying to get on the freeway sometimes, or traffic jams. You think you're never going to get out, but you eventually do. I'm not really sure why, because it seems like the lineup of cars goes infinitely. But let's say this is the exit onto the freeway. Okay, and then here's another ramp into the same situation. Okay, you have an infinite amount of positive and an infinite amount of negative, but it's the rate at which you mix the two that determines where or if you're going to converge to anything. And I like to use this example of mixing hot and cold water in a sink. You have a sink and you have, hot and cold water mixing into the same spigot, and the water is coming out and you're washing your hands. But you can control, using the two knobs, you can control the flow rate of the hot and the cold water coming in, and then you get to determine the temperature. The temperature is a nice 70 degrees or 80 degrees or whatever you choose. It's whatever you choose because you pick the rate at which the hot and the cold water are coming together. And so in that case, the temperature of that water is conditionally convergent. It's convergent only due to your interactions. Of course, in reality, this is capped at something like, I don't know, it's definitely no colder than like 20 degrees, and maybe this is no hotter than 200 degrees. It's definitely not 200 degrees. But I'm just saying, in real life, the water can't be infinitely hot or infinitely cold. But in this case, you have infinitely hot and infinitely cold water, and you're mixing them together to get literally any limit you want. Now we go one step further, and just because we're so attached to our paper and pencils, we say, well, let's go ahead and add them in precisely the order in which they come in the formula that we have written down. And it's just as well because it's the easiest thing to talk about, right? So then you can do these calculations and you can rewrite this and you can say, well, if this is 1 over 2n and this is 1 over 2n plus 1 or whatnot, and you can rearrange this algebraically, you can figure out what this is equal to. Let's go ahead and do that. I feel like doing that. Well, anyway, we have this 1 over the quantity 4n squared plus 2n, and you can go ahead and see what that converges to. Okay, I lied. I'm not really in the mood to do that. But anyway, it goes to natural log of 2. So there you go. And there's other cool things you can find on Wikipedia. And so some things are easier to prove and some things are harder. So I just wanted to give you that little bit of trivia there. Okay, so what is the alternating series test? It means you have alternating terms that decrease to 0. It automatically qualifies you for conditional convergence. You try for the better one. You try to say that something is absolutely convergent, but if you can't, then you go for the consolation prize. So when you say something is conditionally convergent, you're kind of saying it's not really convergent. It's just only conditional. Conditional on the condition that you have control over the order in which the terms are added up. And so it means you really have a pile of positive infinity and a pile of negative infinity to play with, and you are defining the order very carefully in which the terms are added up, and then usually you're going to bundle a positive with its following negative or vice versa, or maybe you'll bundle 4 of them together. But you have to bundle them and add them in a specific order, and you can't skip around. You have to honor the order that's given. In that case, then it converges. And we call this the alternating series test. You can also come to the conclusion that you can say something is at least, you can say the phrase at least conditionally convergent. And that means you've demonstrated that it at least qualifies for the conditional convergence, but you haven't positively eliminated the possibility that maybe it converges in its own right. And that's okay. You can say that you can say a series is at least conditionally convergent. That phrasing is okay. That gives a little bit of information, and you're not claiming more than you know. But if you say it's just conditionally convergent when it's actually could be absolutely convergent, then you're not telling the whole story. So you have to be honest. Just be honest with what you know and what you don't know. So say it's either convergent, it's absolutely convergent, it's conditionally convergent, or you can say the phrase, it's at least conditionally convergent if you're not really sure, but you've proven part of what you wanted to prove. And just general advice for web work, I think you're probably going to see a lot of harmonic series, okay? Because they expect you to recognize that this kind of mess is going to be conditionally convergent, and they expect you to know that this kind of mess, is going to be absolutely convergent. Even though it does have alternating signs, it was convergent before we altered the signs, so it's still convergent. So you wouldn't say this guy is conditionally convergent, you would say it's absolutely convergent, because even if I ditch those signs, it still converges. So just be careful. Those are the most common ones you're going to be asked about. Okay, and I think you're good to go. I think you should do the worksheet, and I'll see you in class. Have fun.